All right, last example here. Let's write an equation from a graph. So a scenic train ride makes trips on an old mining line. The graph shows the distance y in kilometers of the train from the station x minutes after the train ride begins. What equation represents the distance from the station as a function of time? What is the domain? So just to kind of understand as time goes on, you can see the distance from the station. So we're getting, our distance is increasing. We're getting further away from the station. Then at 15 minutes, we must be turning around because we're coming back and getting closer to the station. All in all, in 30 minutes, we are back at the station. So does this graph look kind of familiar to you guys? Have you seen something like this? To me, it looks like an upside down absolute value graph. So our absolute value graphs are f of x equals the absolute value of x, and those look like this. So if you start with your parent function, what are we doing to it to get it to look like this? And also that parent function does go through the origin like that. So let's just make a list of what we think happened. What got it to flip upside down? That would have been a reflection across the x-axis. So we know that it reflected across the x-axis, and it's no longer at the origin. We can see that it reflected across. When it reflects across the x-axis, that kind of puts it down here. So it shifted over, and then it also shifted up. So it shifted to the right 15 units, and it shifted up 15 units. So let's come up with an equation that will have those transformations we just talked about. So if our original function is the absolute value of x, the other thing, how do we know if we had any sort of stretch or compression? Would this side of our absolute value graph be going out further, up closer? So I'll just tell you your parent function would have a slope of 1, up 1 over 1, up 1 over 1, up 1 over 1. If we were to look at this, you can see that it is going up 1 over 1. I mean, we're counting differently on each axis, so the numbers look a little bit different. But if we're going over 15 and up 15, that's up 15 over 15. That is the idea of that slope of 1. And so you are getting, it didn't have a stretch or compression. All right, so let's take our function and reflect it across the x-axis. To reflect across the x-axis, the negative goes out in front of whatever your function is. So now we've got this. We've reflected across the x-axis. How do we shift it to the right? So we're just going to add on the shift to the right. We have our reflection across the x-axis. If you're shifting horizontally, you add or subtract with the x. Now this is your tricky x. We're going to the right. We don't want to put plus 15. We're going to put minus 15. So that's showing a shift to the right. So we've got our reflected across the x-axis. We have our shift to the right. How do we show that we're shifting up 15? Your vertical shift goes on the very end of your whole thing, your whole function. So here's our reflection, here's our shift to the right, and here's our vertical shift up 15 on the end. And this will be an equation for our transformed function over here. And then what is the domain? Well, we can see in our new graph, our domain, we're starting at 0 and we go all the way to 30 with your x's. So your domain is just going to be from 0 to 30, and we are including those endpoints, so we put brackets. There you go.